Firmly tighten the 4 screws at the bottom of the robot. Open the crimp contacts protection cover. Connect the heavy load connecting line to robot. Screw in and fix it. Complete the connection between the robot and the control cabinet. Next, insert teaching pendant connection cable into the teaching pendant connector on the upper right side of the back of the control cabinet and tighten it. Then connect the control cabinet's earth wire, lev wire, and neutral wire to the corresponding circuit in turn. The connection between the robot and teaching pendant and the control cabinet is completed. Upward open the control cabinet switch. Wait for the teaching pendant to start and perform the home point resetting operation. Check whether the 0 scale lines at the joints of each axis of the robot correspond to each other. After checking, the robot can be used normally. Berlanter robot includes robot body, teaching pendant, and control cabinet. Teaching pendant sends the demand to the control cabinet. The control cabinet will drive the robot moving based on the received signal. First, let's see the teaching pendant. Teaching pendant is used to write programs, saving programs and data. At the left rear of the teaching pendant is a USB interface that can be used to transfer data programs, etc. At the rear right is the Enable button. When writing a program, need to press and hold the Enable button to move the robot. This is the front of our Berlanter robot teaching device. The key can switch the operation status of the robot. There are 3 status keys in total. In the middle gear is our main interface. In the left is in the automatic state. In the right is in manual mode. In manual mode you can write and modify program to move robot. In the middle mode you can modify the internal parameters. In automatic mode, robot can operate the program we need. The red button next to it is the emergency stop button of our teaching pendant. Press it immediately in case of operation error. Robot will stop immediately. The black disc on the left is a fine-tuning knob. It can make subtle adjustment to the coordinates of each axis. The orange buttons on the left side are Start, Stop, WJ, Reset, Acceleration, Deceleration in sequence. Start and Stop buttons are used to control a written program and the operation of robot. WJ is for quickly switching coordinate systems. W represents the world coordinate system. J represents the joint coordinate system. The reset button can restore robot actions to the robot standby point. The acceleration and deceleration buttons can control robot running speed. F1 to F5 and the white button are signal binding shortcut buttons. It can be used to calibrate screen test keys or set custom function keys. Act as a shortcut key. On the right side J1 to J is axis button. Control the action of each axis. Teaching pendant can control 8 axes. A typical 6-axis robot will use J1 to J6 to operate each axis. J7 and J8 can bind additional axes. The line below is the signal connecting line between teaching pendant and control cabinet. There is a touch pen on the back for easy manipulation of the teaching pendant. First step is login. You can operate robot and set up the system after login. Different users have different management permissions. Firstly, it is the home screen. Click Login. The first line is User. Click the black triangle. You can see several login methods come with system. The default password and permissions for our system are as follows. Distinguish the corresponding management permissions of different usernames on the system. Refer to the following figure for details. First, shift the key to manual gear. The upper right corner of the teaching pendant will display in manual mode. Next, let's take a look at I/O monitoring. This monitoring page allows for real-time viewing of monitoring related information, including input and output, intermediate variable, servo monitoring, data in memory, welding data, and so on. Click the I/O monitoring pop-up window. Click again. Retract the window. Secondly, we can check monitoring information in the logs. Here we can monitor alarm records, operation records, button records, and alarm record page. Record information on robot abnormal alarms. Record operation record page. Record operational records. Key recording page. Record button or switch operation records. Same as I/O monitoring. Click on the log again to zoom back to programming page. If you want to view or modify the module number, clicking on the module number directly is not allowed to view it. We need to log in first. User select Senior Administrator. Password 1, 2, 3, 4, 5, 6. After logging in, we can view or operate on the module number. For example, creating a new module number or loading a model number. We can also import the module number from USB or export the module to USB. Click on the module number again. Return to the programming interface. In the programming interface, you can view and write programs. We will explain it in detail in the upcoming class content. The robot joint coordinate system is used to control the motion of each joint, and different robot joint types also vary. We can switch coordinates through the WJ button on the left side of the teaching pendant. J represents joint coordinates. W represents world coordinates. Next, let's practice. This is the Bollanter 08056 axis robot. First, log into the Senior Administrator and turn the key to manual mode. We can see that the workbench on the left displays world coordinates. Click the WJ button to switch to joint coordinates. Now, we can operate the J1 to J6 buttons on the right side of the teaching pendant through the Enable button to operate the corresponding axis. We can see that its one axis has a degree of freedom of plus or minus 170 degree. Its two axis has a degree of freedom from minus 98 degree to plus 80 degree. Its three axis has a degree of freedom from minus 80 degree to plus 95 degree. Its four axis has a degree of freedom of plus or minus 180 degree. Its 5 axis has a degree of freedom of plus or minus 120 degree. Its 6 axis has a degree of freedom of plus or minus 360 degree. If you want to move the robot end position to the desired position in the joint coordinate system, it can sequentially move the motion of each joint to guide the robot end position to the designated position. Take the one-axis joint movement as an example. We can set a starting point first. Click Set the End Point. Click Insert. Press J1+. Turn the robot to the point where we need it. Click again to set the end point. Click Insert. Then we come to the automatic interface and run the robot motion between the points we just wrote. We can see that one axis has already repeated its work according to the path we have set up. Cartesian coordinate system used to describe the movement of the robot body based on the robot mounting base. This coordinate system is composed of the mutually perpendicular x, y, and z axes. It is the basic coordinate system necessary for robot motion in three-dimensional space, and it is also the most commonly used coordinate system. We can use our fingers to distinguish the direction of the x, y, and z axes. Operator facing the robot and extends left hand to gesture, facing yourself with middle finger. The middle finger represents the x-axis for controlling the forward and backward robot motion. The index finger is horizontal, representing the y-axis for controlling the left and right robot motion. The thumb is facing upwards, representing the z-axis for controlling the up and down robot motion. Next, enter the practical operation. Turn the teaching pendant to the manual interface. We can see that the workbench on the left usually defaults to the world coordinate system. If not, we can switch through the WJ button. The positive and negative J1 to J3 buttons on the right correspond to positive and negative XYZ. X negative is for controlling a backward robot movement. X positive is for controlling a forward robot movement. Y negative is for controlling a leftward robot movement. Y positive is for controlling a rightward robot movement. Z negative is for controlling a downward robot movement. Z positive is for controlling an upward robot movement. If we want to move the robot to point A, first, set an initial position, click Set the End Point, click Insert. Then we use world coordinates to move the robot to point A. Click Set the End Point again, click Insert. Turn to the automatic interface to move. This is how the robot motion between points is achieved. Through world coordinates, instruction can be understood as a control command that enables a robot to move to a specific position. The motion instructions of Bollanter robot is mainly divided into 5 types. They are posture straight line, postural curved line, free path, posture rounding and relative instruction. Before learning the specific contents, we have to know the 3 factors affecting instruction speed. The first factor is axis speed. Axis speed refers to the maximum speed set by the servo of each joint of the robot. It can be found in the product introduction on the official website or the product technical recommendation. The second factor is path speed. Path speed refers to the speed multiplier set in a single path program line. It can be understood as when robot moving on a trajectory, the percentage of axis speed on this trajectory. The path speed can be modified when path programming. The third factor is speed multiplier. It is the percentage of the robot's entire speed. We can click on the upper left corner of the teaching pendant to view it. The default setting is 10%. That is 10% of the robot's axis speed, which can be changed according to actual application scenarios. Above 3 factors: axis speed, path speed, speed multiplier determine the actual operating speed of the robot. When we want to measure the actual speed of a robot at a certain joint or in a straight line, we can use maximum speed multiply path speed multiply speed multiplier. This formula to calculation. During normal operation, we can control the speed of robot movement by changing the path speed or speed multiply bands. It is using joint interpolation method to move to the teaching position. The speed of each joint follows: axis speed multiply path speed multiply speed multiplier. To operate, we can tick free path fit, editor, S per age, path. To operate robot movements, the right option box are all parameter settings for free path. We can first look at the 2 options above: set endpoint and input endpoint. Set endpoint is directly records the current joint position coordinates of the robot. Input endpoint need to fill in a joint position coordinate of the robot yourself. These 2 methods are selected and used according to the actual scenario needs. Below has a select point. It can reference previously created joint positions. After ticking, directly insert the point data. We can enter the point setting interface by clicking the green button in the bottom left corner. Click Set in Joint Position. Create a new joint point, and we have recorded a reference point. Smooth level refers to the smoothness of the connection between points during the robot's movement process. Default is no smooth. We can see that when the smooth level is none, the robot will move to the set point position and move to the next point. After set smooth level, the robot will transition the set points in a smooth manner. It can reduce pauses between points. There are 10 levels of smooth. The higher the smoothness, the lower the accuracy of the trajectory. The robot moving position is most accurate when there is no smooth. The speed is the path speed. It is the speed multiplier set in the single path program line. Delay is when the robot reaches the finish line. It will wait for n seconds. The default action is 0 seconds. Above are all the parameter settings for the free path. When choosing free path, it is necessary to pay attention to its motion trajectory characteristics. It is actually presented in arc, but if the 2 points you set are straight lines and choose a free path, the final effect presented is still in arc. It is due to there is only an angle operation relationship between the points in the free path. The posture line is also the most commonly used instruction in motion commands. It is using linear interpolation method to move to the teaching position. The speed of each joint follows: maximum linear speed, multiply, path speed, multiply, speed multiplier. To operate, we can tick posture line in, editor, S per age, path. To operate robot movements, the right option box has set, endpoint, input, endpoint, smooth level, speed, delay, select point. 6 parameter settings, tick input, endpoint. The interface displays the settings of the X, Y, Z, U, V, and W coordinate axis parameters, except the axes parameters display is different from the joint parameters in free path. All other parameter settings are consistent with the definition in the free path. Next, let's see the actual trajectory effect presented by the posture line. Let's first move the robot to the desired starting point through teaching. Tick posture line in program, editor, S, H, tab, tick set, endpoint, and insert it. The starting point is set, and write an endpoint using the same operation. After writing, let's make it run automatically to observe its trajectory. The trajectory characteristics of posture line and free path are different. The posture line is between points and operates in a linear interpolation manner, so its trajectory features a straight line. The main factors that affect the robot's straightness are the deceleration ratio, link parameters, origin point and motor rotation direction. If the above parameters are incorrect, it will cause the robot to walk in a straight line imprecisely or produce tilting phenomena to the teaching position. The speed of each joint follows maximum linear speed multiply path speed multiply speed multiplier to operate. 3 points can determine an arc. If you want to maintain robot posture path in an arc, you need to establish a tool coordinate system to ensure the accuracy of trajectory during arc transformation posture. We can take posture curve in program editor S/H path to control the robot to follow an arc trajectory. The right option box asks select point, smooth level, speed, and delay. Setting has the same definition with free path. Setting the posture curve, need to determine 3 points. They are start point, midpoint, and end point. 3 points form a complete curve. First, the start point can be determined through a free path or posture line. Then tick posture curve, set or input point information for midpoint and endpoint. After determining the information of T3 points, we can test the motion trajectory of the robot. 2 points need to pay attention when setting posture curves. 1. Setting a continuous curve doesn't require setting a start point again, because the end point of the previous curve is the start point of the latter curve. 2. When setting curve with posture or continuous curve, it is necessary to choose the tool coordinates with accurate calibration. Without selecting tool coordinates, it is impossible to create a posture curve effect. Circle is using full circle interpolation method to realize a complete arc trajectory. The speed of each joint follows maximum linear speed multiply path speed multiply speed multiplier to operate. We can tick posture circle in program editor S/H path. To operate robot draw circles, there are 2 methods to set posture circle, 3-point way and the center way. The 3-point way is to determine a circle based on 3 points. Its operation method is consistent with the posture curve. It is also set the start point through posture line or free path, then set the midpoint and end point through posture curve. These 3 points can form a complete circular trajectory. Center way is achieved by determining the circle center, radius, start point reference point P1, and flat reference point P2. To draw a full circle, the right option box asks SSE, MSE, T1 start point reference point, T2 flat reference point, the radius below, direction. Return to the circle center at the end. The circle center and radius determine position and size of the circle. T1 point is the reference point for drawing the starting path of a circle. T2 point is the reference point of the screen plane. There are clockwise and counterclockwise directions. Default is clockwise. Returning to circle center at the end refers to the robot automatically returns to the center position after drawing a circle. Default is not returned. You need to tick this option to return. After setting the above parameters, robot will start from the circle center, run in the direction of P1 to the radius point. Draw a circle clockwise in the plane, determined by the center of the circle and points P1 and P2. It should be noted that, if the z-axis heights of P1 and P2 are inconsistent, robots can walk on an inclined plane. The above parameters need to be set in the world coordinate system. The instruction is for the robot to move in its current position based on the relative value of the motion mode. We can tick relative and posture line or posture curve line or free paths in editor S per H path to operate the robot in relative motion. Here, we cannot select input the point position in the point position setting of relative instruction. We can only fill in the input point position manually. We must review and understand the previous courses on setting up posture lines, posture curve line, and free paths in advance. Relative instructions combines the operating characteristics of 3 motion instructions. Calculate the specific motion position of the point by inputting the relative value data of the point, thereby achieving the relative point motion of the robot. For example, the relative free path. Tick relative and free path, and click on the right input the endpoint option box. Here will appear the setting of J1 to J6. Assuming we input -20 degrees on the J1 axis, and input 20 degrees on J5 axis. To test run the program. robot will move 20 degrees in both the negative direction of the J1 axis and the positive direction of the J5 axis, based on the current point position. When the robot runs in the next cycle, it will continue to move 20 degrees towards the negative direction of the J1 axis joint and the positive direction of the J5 axis simultaneously, starting from the current point position. This is the relative free path. Next one is relative posture line. Tick relative and posture line. Similarly, input the relative value for setting the endpoint. Assuming we input -50 on the x-axis, robot will move a distance of 50 millimeters towards the negative x-axis of the world coordinate at its current position. If you want robot to move a relative gesture, you can run the robot to move in a relative gesture by setting the relative values of the u, v, and w axes. The same operation applies to relative posture curve line. Firstly, we set the starting point position through a posture line or free path. Then tick relative and posture curve line. Click input midpoint and endpoint. Input the relative value of the point position on the XYZUVW axis. Finally, test run the robot. We can see robot moves to the midpoint by calculating relative values from the starting point. Then calculate the relative value data from the midpoint and move it to the endpoint. D is the operation of relative posture curve line. It should be noted that, when using relative posture line or relative joint instruction, if robot stops midway and restarts, it will continue to move the set relative instruction value. Using the stop position as a reference point, the tool coordinate is based on the tool center point as the 0 point. The robot trajectory will move with reference to the tool center point, because robots often install suction cups, welding guns, cylinders, and other tools on the flange during actual movement. Taking the welding gun as an example, its structure is generally curved so that for the convenience of programming, we need to set a tool coordinate system for it. After setting up, we can easily use the end of the welding gun as the origin for programming and better edit the trajectory path. There are various methods for calibrating tool coordinates, such as 2-point method, 3-point method, 6-point method, and 23-point. We will provide a detailed explanation in the following classes. The 2-point calibration method can only be used when the coordinate values of the tool and in the flange coordinate system are known. Click Operation and Tool Calibration. Here we can edit and modify the established tool coordinates and create a new tool calibration. After establishing the name, choose the 2-point method calibration type. Click on the newly created tool and enter the calibration interface. First, move the robot to the origin point and click T-set. Next, input the values measured by the tool in the XYZ direction from the end of the tool to the center point of the flange into the tool deviation. Click Count and Save. Then we have set a tool calibration through 2-point method. It should be noted that 2-point method is only suitable for low precision situations. 3-point calibration method is generally used for tool calibration of 4-axis robots, calculated from 3 posture points 0, 1, and 2 with a pose angle greater than 30 and a tool end infinitely close to the reference cost. Create a new tool calibration and choose 3-point calibration method. We can see on the right are the points 0, 1, and 2 that we need to record. Record 3 points through programming. It should be noted that the posture angle must be greater than 30. After recording each point, click Count and Save. Then we have set a tool calibration through 3-point method. 6-point method is a commonly used tool coordinate calibration method for 6-axis robots. This method requires selecting a reference cusp and recording 6 points to calculate the tool coordinates. The 6-point method is composed of 3 posture points 0, 1, and 2 with attitude angles greater than 30 each other, and tool tip infinitely close to the reference tip, and a posture point with tool z-axis parallel to the world z-axis, and tool tip infinitely close to the reference tip A, as well as 2 points B and Z in the x-axis and y-axis directions with the same posture at reference point A. Let's demonstrate how to create a tool coordinate in 6-point method calibration. Click to switch to the newly created tool coordinates. We can see on the right are the points 0, 1, 2 and points A, B, C we introduced earlier. Turn to the manual mode. Record 6 points through world coordinates. It should be noted that the tool end should be infinitely close to the calibration point in order to ensure that the calculated tool coordinates are accurate enough. Be careful when handling to avoid colliding with the robot. After recording 6 points, click Count and Save. Then we have set a tool calibration through 6-point method.